In this video, we're going to talk about linear independence of functions using something called the Wronskian. So recall that two functions, f1 and f2, are linearly independent if and only if neither one of them is a multiple of the other. So I'll say neither f1 nor f2 is a scalar multiple of the other. Scalar multiple of the other. All right. So we've been talking about differential equations, and we've looked at this example in a previous video where we had y double prime minus 8y prime plus 16y equals 0, and we found that this had solutions. So the function e to the 4t was a solution, and the function t times e to the 4t was also a solution. And we talked about the fact that we wanted to find two linearly independent solutions to this differential equation, because a second order homogeneous equation like this, the set of solutions should be two-dimensional. So I should be able to find two linearly independent solutions to it. So the question that I want to focus on is, why are these two functions linearly independent? So there are two main reasons that I can give. So the first is, well, using our definition of linear independence, neither one of these functions, neither is a scalar multiple of the other. So it is true that y2 is the first function times t, but that's not a scalar multiple. So that doesn't count. That wouldn't count as being linearly dependent. All right. So with two functions, it's pretty easy to tell just by looking at them if they're linearly independent or not in general. But we'd like a way to be able to test for independence or dependence even if we had more functions. And with more functions, it's harder in general to check if they're linearly independent or not, purely by using the definition of linear independence. So one of the ways that we kind of got around this, how we tackled this problem before, was with polynomials. With polynomials, we would sometimes convert the polynomials to coordinate vectors. So we would convert them to coordinate vectors relative to the standard basis of Pn. But the issue with that, and what we are trying to do now, is we can't do this with infinite dimensional vector spaces, with infinite dimensional vector spaces like C infinity. So C infinity is the space of infinitely differentiable functions. And that's what we're working with here. The set of solutions to our homogeneous differential equation, that's a subspace of C infinity. So that's what's going to make this coordinate vector approach difficult, because we'd have to form an infinitely long vector. All right, so here's what we want. We want a systematic way to test if solutions to ODEs, to our ordinary differential equations, ODEs, are linearly independent, if they're linearly independent or not. So this will take me to reason 2, another reason that we can get, another way we can show that those two functions were linearly independent. So we're going to introduce something. We're going to use something called the Wronskian. So we're going to use the Wronskian. Okay, so let's give a definition of what this thing is. So the Wronskian of two functions, y1 and y2, is defined as the following. So on the left-hand side of this equal sign, this is my notation for the Wronskian. So the Wronskian is a function that'll input two functions. It'll input y1 and y2, and what it'll give us out is this determinant. So that's what these vertical lines mean. This is a determinant. And the first column has the original function y1, its derivative underneath that, so y1 prime. The second column is the same thing, but with a second function. So y2 and then y2 prime. And then I've gone ahead and written out what the formula is for a 2 by 2 determinant. So we'd get y1 times y2 prime, so multiplying these two, and then minus y2 times y1 prime, so multiplying along that other diagonal. All right, so this is y2. Next, I want to state a key lemma. So a lemma is sort of like a smaller theorem that will connect how this Wronskian is useful for testing if solutions to ODEs are linearly independent or not. So here is the lemma. It says that if y1 and y2 are solutions to ay double prime plus by prime plus cy equals 0 on the interval from negative infinity to infinity, so they have to be solutions everywhere, then the Wronskian of those two solutions is 0 for some value of t that we can plug in. That's true if and only if the two functions y1 and y2, those two solutions, are linearly dependent solutions. So if the Wronskian is 0 even at one point for some t, that'll mean that the two solutions are linearly dependent. On the flip side, if the Wronskian is not 0 for all values of t, then y1 and y2 are linearly independent solutions. So it turns out that we can say something even slightly stronger and something slightly more definitive than this, so we don't have to worry so much about the for some t and the for all t, and that's the theorem that I want to state next. Here is this next theorem. So again, if y1 and y2 are solutions to our differential equation, and it is really, really important that y1 and y2 are actually solutions to this differential equation. That was even the case in that Wronskian lemma that we just stated before this. And these are solutions everywhere on the interval from negative infinity to positive infinity. It turns out that if the Wronskian of those two solutions is 0 for some value of t, this will imply that the Wronskian of those two solutions is 0 for all values of t. So that is pretty cool. That's pretty cool that if it's 0 for even one value of t, it'll be 0 for all values of t for these two solutions when I take their Wronskian. And the second condition is, well, that's true even if the Wronskian is not 0. If the Wronskian of our two solutions is not 0 for some value of t, even one value of t, that will imply that the Wronskian is actually not 0 for all values of t. All right, so let's look at an example. So let's go back to our example of this differential equation. Y double prime minus 8y prime plus 16y equals 0. And we've seen that this has these solutions, e to the 4t and then t times e to the 4t. So let's now answer the question, why are these two solutions linearly independent by using the Wronskian? So first off, we know that y1 of t, which is e to the 4t, and y2 of t, which is te to the 4t, that these are solutions. These are actually solutions to an ODE. So that lets us apply our theorem about Wronskians. So our two functions need to be solutions to our ODE to be able to apply that theorem. All right, so let's form the Wronskian now. So the Wronskian, so W bracket y1 comma y2 bracket parentheses t will be the determinant. So I'll have y1 first, and then its derivative underneath that, and then y2 after that, and then its derivative underneath it. And now let's plug in what these are. So y1 is e to the 4t. its derivative is 4e to the 4t. y2, the second function, is te to the 4t. And the derivative of that involves the product rule. So we get first times the derivative of the second. That'll give us 4te to the 4t. And then plus the second times the derivative of the first, derivative of t. So that'll just give us plus e to the 4t. That's what we get from doing the product rule. All right, so now let's evaluate this determinant. So doing this, first we have to multiply these two entries. So we'll get e to the 4t times 4t e to the 4t plus e to the 4t. And then minus what we get from multiplying the other two diagonal entries. So minus, what do we have? So we have 4e to the 4t being multiplied by te to the 4t. So let's continue to simplify. So notice that after this, if we were to distribute e to the 4t into the two terms that we have in this parentheses, so also this is a t right here, one of the terms is going to cancel with this 4e to the 4t times te to the 4t. In fact, what will cancel? Notice that this, when we distribute it to that, will perfectly cancel away with this term right here. So what we will be left with is what we get from distributing e to the 4t to e to the 4t. So we will get e to the 4t times e to the 4t, but multiplying these, we have to add the exponents. This is e to the 8t. So that's what our Wronskian is. And now we want to know, is this 0 or is this not 0? So this is actually not 0. E to any power is not 0. And it's definitely not 0 for every single value of t, for all values of t. So when that happens, that means our two solutions, so our two solutions were e to the 4t and te to the 4t, they are linearly independent. So we've used the Wronskian to show that they are linearly independent solutions to our differential equation. So at this point, it might not look like the Wronskian is particularly useful. Like this computation seemed to be harder than just stating that these two functions were linearly independent just by kind of looking at them. But where it's really going to be useful for us is when we have more than just two solutions. And later in the differential equations part of the class, we'll talk about how do we solve a system of differential equations. So not just one like this. And that's where Wronskians are going to be especially helpful for us in determining whether our solutions are linearly independent or not. All right, so next I want to state a key warning. So the warning is the Wronskian being equal to 0 only implies that our functions are linearly dependent if the functions y1 and y2 are actually solutions to a homogeneous ODE. If they're not solutions to a homogeneous ODE, the Wronskian being equal to 0 might not tell us any information. So that is super, super important. It's important that these functions are actually solutions to a homogeneous ODE. So I want to do an example to illustrate why this is important. So let's say we have these two functions. y1 is t squared and y2 is t times the absolute value of t. So these two functions, just by looking at them, they are not scalar multiples of each other. So these should be linearly independent, just by sort of inspection, by looking at them. But now let's figure out what the Wronskian is. So for this absolute value term, let's write this as a piecewise function. So notice that the absolute value of t, so recall that the absolute value of t can be written as a piecewise function, is equal to t if, actually let's give myself a little bit more room here. So the absolute value of t would be equal to t, I can just drop the absolute values, if t is greater than or equal to 0. But if t is less than 0, the absolute value will end up being negative t. Because if t is less than 0, that means t itself is negative. And putting another negative in front of it will make it positive. And that's what the absolute value is supposed to do. It's supposed to make negative numbers become positive and keep non-negative numbers the same. Okay, so for that reason, t times the absolute value of t, there will be two cases. If t is greater than or equal to 0, and if t is less than 0. And if it's greater than or equal to 0, this will be t squared. If it's less than 0, we'll get t times negative t, and that's negative t squared. So our Wronskian will also be a piecewise function. That's okay, we can handle this without too much trouble. It'll be just fine. But now let's look at the Wronskian. So the Wronskian of y1 comma y2, and then I put a parentheses t. So I have to form my determinant. So I have y1 and then y1 prime, y2 and then y2 prime. So our determinant depends on which piece of y2 we're looking at. So we're going to have to write this as a piecewise function. So this will be a piecewise function. So sometimes y1 is always t squared. Its derivative is 2t. And now for y2 is sometimes t squared in this top piece. And if it was t squared, its derivative would be 2t. So that's what the Wronskian would be equal to if t is greater than or equal to 0. But it could be equal to one other possibility. So the first function is still t squared. Its derivative is still 2t. But if y2 was negative t squared, then its derivative would be negative 2t. So that's going to be the case if t is less than 0. So we have these two determinants. And it's really quick to check. It's really quick to check that this first determinant will end up being equal to 0 if we just do it. It's going to be equal to 0. This second determinant, same thing. It will also be equal to 0 after we work it out. And it's really quick to do. All right, so the takeaway from this is, notice that the Wronskian of our two functions, y1 and y2, of t, equals 0. It equals 0 for both of these cases. So that means it equals 0 for all values of t. And typically, that would mean our two functions are linearly dependent when the Wronskian is 0. But y1 and y2, we said at the beginning, are not linearly dependent. They are linearly independent. And the reason why this happened is because these two functions, y1 and y2, they're not necessarily solutions to a homogeneous ODE. If they were, then their Wronskian would not have been 0 because they're linearly independent. So that is a super important warning. Next, what I want to do is I want to state a theorem that talks about, well, what if the Wronskian is not 0 and our two functions, y1 and y2, are not necessarily solutions to a homogeneous ODE? What if they're just arbitrary functions? This theorem says the following. It says that if the Wronskian of two functions, y1 and y2, is not 0 for some value of t, then y1 and y2 are linearly independent. So this is true for even arbitrary functions. So for arbitrary functions, so they don't necessarily have to be a solution to an ODE, if their Wronskian is not 0 for even one value of t, then those two functions y1 and y2 are linearly independent. All right, so we've stated a bunch of facts about Wronskians. I want to organize them into a table. So based off of two categories, whether our functions are solutions to ODEs or whether they're arbitrary functions. And then also keep track of, well, what does it mean if the Wronskian is 0 for some value of t? And what does it mean if the Wronskian is not 0 for some value of t? So when we're talking about solutions to ODEs, so when we're talking about this column right here, our Wronskian lemma applies. So the Wronskian lemma that we talked about earlier in this video will apply. this applies in this column. Okay, and what it says is, if the Wronskian of two solutions to an ODE is 0 for some value of t, even just one value of t, that'll automatically mean that the Wronskian is 0 for all values of t. So that's true when our functions are solutions to an ODE. And in that case, the functions are linearly dependent. They're linearly dependent when the Wronskian is 0 for all values of t. Okay, and then when the Wronskian is not 0 for some value of t, as long as our functions are solutions to an ODE, this will imply that the Wronskian is 0 for all values of t. And if that's the case, that means our functions, our Wronskian is not 0 for all values of t, right? Because this was saying not 0, this should also say not 0. So because it's not 0, that means that our functions are linearly independent. Linearly independent. Okay. The previous theorem, so the one that we had before this, says that if the Wronskian is not 0 for some value of t, even if the functions are arbitrary, they're still going to be linearly independent. So in this slot over here, the functions are linearly independent. So even if they're arbitrary functions, as long as the Wronskian is not 0 for some value of t, they are going to be linearly independent. So this is true by the previous theorem. So by the previous theorem. But when we have arbitrary functions and the Wronskian is 0 for some value of t, that gives us no information. So this gives us no info. So that's usually the scenario that we have to be very, very careful of. So no information. And if there's no information when we plug in this value of t, well then we either have to use the definition of linear independence or check a different value. Check a different value. Plug in a different value. So maybe we just got unlucky with the value that we plugged into the Wronskian and got that it was 0, which yields no information for arbitrary functions. So we might have to just check a different value. And maybe by checking a different value, the Wronskian would end up being not 0, because that would mean that they're linearly independent. All right, so now let's just highlight these a little bit. So for the solutions to ODEs, let's highlight those all one color, because this is sort of a special case when our functions are solutions to ODEs. And then let's also highlight this section when we're talking about arbitrary functions. When the Wronskian is not 0 for some value of t, it yields very powerful information. The only situation we have to be careful about, especially careful about, is this one right here. And be careful that when we have arbitrary functions, the Wronskian being 0 at some value of t doesn't give us any information.